Next problem is called combination sum 2. We are given a collection of candidate numbers called candidates and the target number target. We have to find all unique combinations in each in candidates where the candidate numbers sum up to target. So we have to pick a combination, unique combination, and return all of them that fulfill the requirement that when all the elements inside that combination are summed up, the sum is equal to target. There's a additional requirement that each number in the candidates may only be used once. So in the combination sum 1, we didn't have this requirement. We could have used any numbers several times. There was no restriction of this nature in the previous problem. There's also the solution set must not contain duplicate combinations. So in the first example, the target is 8, and as you can see, we have 1 and 1. They are both present in the array, so we are not repeating numbers. They are present in the frequency of 2, and then number 6 is present 1, and that 1 plus 1 plus 6 is equal to 8. Then we have 1, 2, and 5, which is again equal to 8, and then the last two pairs is 1 and 7 and 2 and 6. For the second example, we basically have the same. We can combine 2 2s and a 1, or we can just combine one element, which is 5. So we are getting two combinations that sum up to 5. The length of the candidates that you can choose from is ranging from 1 to 100, and all the elements inside the initial set of candidates are ranging from 1 to 50, and the target is from 1 to 30. Now, there is this problem, if you went over the last problem, combination sum and permutation, subsets, and so on, all the other problems in the backtracking category, this problem should be pretty straightforward, because we can use the two tricks that we have learned to solve the problem. Basically, we will reuse almost the same code as we had for the combination sum 1. We just have to first, we cannot use number more than once, and to solve that problem, that's the first problem, not repeating the numbers, we will just speak the for loop inside our helper function to always start in the next position. So when we are calling our helper function, the start for the next recursion call of the helper function will be I plus 1. So we will not be able to use all the previous elements. And the second problem is basically the no duplications, and we already faced that issue several times in permutations 2, subset 2. So this should be easy. We just basically sort the initial array, and then for each element we check if the previous element is the same. If it's not, we can freely use it. But if it is, we have to check if the previous element has already been used. If it has been used, then that makes a distinct combination. But if it hasn't been used, we cannot use the same element that we have at this next index, because that will lead to duplicates. So combining these two properties, we will be able to solve the problem. As always, we will start by declaring our list of lists, which will present our final output of the main function combination sum. This is basically our list of combinations that we have managed to generate that fulfill the requirement that they sum up to the target given by the input. Next, we will sort the initial array of candidates. This is the first step to help us prevent duplication in the output. We will call the helper function, and then after the helper function execution is completely done, all the recursion, we enter the whole recursion tree, we just return the result. For the helper function, we are passing the candidates array as the first parameter. So these are the elements that we can choose from. The current sum that we have to, basically we summed up so far, choosing some of the candidates. The target, that it's basically our final destination. The current sum and target have to match for us to use the current list, which represents our combination that we are currently generating, to add it to the result, which is the list of all the valid combinations. There are two additional parameters: start, which basically is our index, where we are starting each call of the recursive call of the helper function. And we also have the array of Boolean named selected, which will help us to determine if the previous element has been selected. So we are bypassing duplicates. And next we have the base case. If the current sum is equal to the target, we just basically copy the current list to the list of list, which is represented by our result parameter. And we return up in the recursion tree. Next, we will do a for loop, and as you can notice, it doesn't start from 0, it starts from the start. So in any successive helper function calls, we will not be able to choose the elements that we have chosen in the previous helper function call. That will help us to only use the elements in the combination once. And now to solve the second problem of duplicates, we will first check if the target is still larger than the current sum when added the contribution of the current candidate, because if it's smaller than it, then there's no reason for us to go any deeper into the recursion tree. So we are only checking if we are matching up to the target or like the target itself, if the current sum plus the candidate is equal to the target. In that case, we will converge to our base case and add the list and add the current list to the final result. To prevent the duplicates, we will first check if you are starting for I is equal to 0, so this is the first element that you are choosing, or if the current element is not equal to the previous element. In that case, we can freely use it. Or in case it is the same, we have two adjacent numbers, and we want to be sure that we have selected the previous one, so we can be sure that there will be unique combination in the final output. To do that, we are using the selected Boolean array, and if it's true, that means that the previous candidate has been selected in this combination that you're currently generating. If the conditions are fulfilled, we add the current candidate, we make it selected, just turn the index element at the index I in the selected Boolean array to true. Then we basically call the recursive helper function, only changing the start to I plus 1, so it can start from the next element. Everything is passed as it is. Besides, also we have the current sum plus the contribution of the current candidate. After we are done, we have to backtrack and we remove the last element that we have added before calling the helper function, and we make it the selected index the element at the in current index in the selected array, Boolean array. We have to change it to false, so we basically unselect it. Now for the time complexity, basically we can have at most n selected elements, and for each element we have two options, either to select it or not selected. So it's basically a power set problem. So we have n times 2 to the end. Now for the space complexity, because we can have at most a list of n elements. So basically we selected all the candidates and they add up to the sum. So for example, we have 5 ones and the target is 5. We would add just all the elements, and that would be the only combination possible. So in that case, we will have the current list will be of the length n. So the space complexity is proportional to the number of elements that we have in the initial candidates array.